Yes, class. Good evening. Is this audible?
Good evening, ma'am. Yes, it's audible.
Okay. So in the last class, we had covered this topic, resistance and resistivity. First, tell me, how many of you received the assignment of this topic? You didn't receive this topic, not drift velocity and Ohm's law. This one, resistance and resistivity. Did you receive or not? Yes, Kulsum?
Velocity was the last assignment we received, ma'am.
And what that was the last assignment.
Ma'am, the assignment you're talking about is uploaded today, I guess. Just today.
You have received it today.
Yes, sir. Yes, ma'am.
Okay, fine. So, just complete it, and in the next class, then we discuss it. Resistance. Basically, it's the opposition to flow of charges, which we had seen. According to Ohm's law, it is V by I. So we had seen the formula of resistance. This is important. This is important for today's class as well. So R is equal to ml divided by Ne square A tau. M is the mass of electron. L is the length of the conductor. N is the number density. E is the electronic charge, 1.6 into 10 to the power minus 19. A is the area of cross section. Tau is the relaxation time. Now, this is important. Resistance depends on length. Resistance is inversely proportional to area of cross section. It depends on nature of material and temperature. Now, as I told you on the last class, that how does it depend on temperature, that we'll see in detail. So that we'll see in today's class only. How temperature affects resistance. Resistivity is basically resistance for unit area for unit length. Resistivity, you can say, it is M divided by Ne square tau. So L and A gets eliminated. Now let's see this. Let's start with a few 4 topics also we had seen: conductance, conductivity, mobility, and current density. Now temperature dependence of resistance and resistivity. Now why did I write it together? The reason is that formula of resistance, this is ml divided by Ne square A tau. Resistivity is what? Just eliminate L and A. It is M Ne square A. Not A tau. That is the formula. So from here we can see what? This is tau. R is directly dependent on what? Length and area. And resistivity is not depending on either length or the area. So what happens for a temperature range, for a certain temperature range that you have, length and area do not get affected because of it. There is not such a significant change in either length or area. That's why whatever are the resistance, whatever are the changes in temperature, how will it be affecting the resistance? In the same manner, it will be affecting resistivity. See, if I tell you there's a difference between resistance and resistivity, you can easily say L by A is the only difference. Otherwise, rest of the terms are same. If I say L and A is constant, both L and A are constant, then you can also say resistance on what all factors will resistance will be depending on, resistivity will be depending on the same factors. Just the difference of L and A comes. So if I say length and area are constant, then resistance and resistivity, the difference will vanish. So whenever we'll be considering all the temperature changes, no, length and area won't be affected much. So that's why all the changes that we'll be seeing for resistance, those are valid for resistivity. This I'm telling because if I do not tell what's the variation in resistivity, just take it as the same variation in resistance of a particular material. So for the temperature range, whatever is the temperature range involved, there is no significant change in length and area. So resistance and resistivity, both of them will show the same variation. Now, this was a general point that you should just keep in mind. Now, let's talk about all the materials. See, temperature dependence, this is more in detail in your that lesson, semiconductors. Semiconductors will also be repeating the same thing. So this is important for your last chapter also. Semiconductors is your last chapter of class 12th in your second book, part 2 NCRT. Now, conductors you already know. Conductors we have discussed in the class. Conductors are what? Conductors are basically materials that allow electrons to pass through them. So in case of conductors, what happened? As you increase the temperature, whenever temperature gets increased, it decreases the relaxation time. Means tau gets decreased. Now, according to the formula, if you remember, resistance, resistivity, both are inversely proportional to tau. So if the tau is decreasing, it means resistance and resistivity will increase. So resistance or resistivity both will increase. So as you increase the temperature, resistance and resistivity will increase. And if you decrease the temperature, resistance and resistivity will decrease. Reason, because it is inversely proportional to tau, and tau is inversely proportional to temperature. One more thing, in the formula you can see it is also inversely proportional to number density. N is coming in both of them. Reason that we are not considering N is that whenever temperature increases, N remain constant. Number density is almost constant. So on increasing the temperature, resistance and resistivity, this only increases. Let me write down that also. On increasing the temperature, the resistance or resistivity increases. And vice versa, that also you consider in mind. If temperature decreases, then tau will increase and resistance and resistivity will decrease. Now, apart from this, one more thing that you have to remember is the graph. Graphs will be involved. See, if I plot a graph between resistance and resistivity versus temperature, let's take temperature in Kelvin. So initially what happens, the growth is in this manner, means non-linear. You can see this is what kind of growth. This is non-linear. Non-linear. This is non-linear. So initially from 0 degree, from your origin of the graph to a certain value, difference or variation of resistance and resistivity with temperature. This is non-linear. Now, what is this temperature? This temperature is 273 Kelvin or 0 degree Celsius. Up to here, it is non-linear. Then afterwards, it is linear. This is linear. Therefore, you can directly say that up to 0 degree Celsius, variation is non-linear. Beyond 0 degree Celsius, it's linear. This is for conductors. Then you have alloys also. Alloys we'll also see. You don't have to do semiconductors and insulators in detail right now, because you already have a whole chapter on it, whole unit you have for electronics. So there we'll see it. But right now we'll also discuss it. So do one thing, first note down these few points, then we'll do for alloy and other materials. Next material that you have is an alloy. So alloy, you already know, mixture of materials. Now, resistance and resistivity. This is a similar case to what we have studied just now. In conductors, what happened? If you increase the temperature, the resistance and resistivity also got increased. In case of alloys also, this is valid, that resistance and resistivity both will increase. But just the difference that makes alloy different from conductors is that in alloy, the significant increase is very less, or the variation is very small with temperature. So that's the difference. Resistance and resistivity will increase with increase in temperature. Difference is what? Variation is small. Difference is that the variation, this is small. So that you can see by plotting the graph as well. If you plot the graph as well of it, see, you will see both of it getting increasing. For example, if I say this is the graph, this is the y-axis with resistance and resistivity. This is the temperature in Kelvin. Graph will be in this manner. In this manner. See how it's different. It's different in the manner that had I drawn this straight line, graph would have been constant. So you can see this slight variation. This is the slight variation which you are seeing. So that's why we draw the graph in this manner. So I'll give you a conclusion with all the materials that you have. Semiconductors and insulators you will study in detail when you will be studying semiconductors, but let's discuss it also. And what's the difference between a semiconductor and an insulator? All this is involved in your syllabus. Semiconductor and insulator. So both of them are inversely proportional. If the temperature increases, the resistance and resistivity, both of them will decrease. Reason is that here the dominant factor is N. N means the number of density. That's why when temperature increases, it affects the resistance and resistivity. So graph will be in this manner. Resistance and resistivity, this is temperature in this manner. Both are inversely proportional. So if I write a conclusion, see, conductors, what we did alloy and we did semiconductors or insulators. If temperature increases, if I increase the temperature in all of them, in case of conductors, resistance will increase. In case of alloy, resistance will increase. In case of semiconductors and insulators, resistance will decrease. This what you have to remember for your theory questions. Just remember the dominating factor. The dominating factor here is tau. Here it is N. N means the number density. One more material, you can remember it for your knowledge. Those are superconductors. I'll write them also. Superconductors. Superconductors are certain materials that practically have zero resistance. So then the conductors only at a certain temperature become and gain superconductivity. So when you draw the graphs, between these superconductors, resistance or resistivity versus temperature, what happens initially at a certain temperature, there is a variation of resistance and resistivity. Means at a certain temperature, resistance and resistivity keep on increasing. Means the temperature will remain the same. Let's say this is the same temperature, the resistivity is value. At the same temperature only, which is known as the critical temperature. It is known as the critical temperature. So at this temperature, resistance only increases, but temperature's value remains same. Beyond critical temperature, the variation is exponential. non-linear in this manner. So this is the graph of superconductors which you should remember. Now, this is all the theory part, how resistance increases, how resistance decreases. But how will you calculate resistance and resistivity, particular formula of it? If I tell you what is resistance, what is resistivity, I give you certain temperatures for it, then how will you calculate it? How will you calculate the value of it? So by looking at this, all these structures, you will be able to just analyze whether resistance will increase, whether resistance will decrease. But you should know a variation, particular variation of resistance with temperature. If you have different values of temperature, you now know for different materials whether it will increase, whether it will decrease. But how to calculate it? For the calculation, you don't have any derivation in this, just a simple straight formula that you have. This is RT is equal to R naught 1 plus alpha T minus T. Let me explain you this formula. RT is the resistance at a temperature. Or let me tell you first the temperature. This is temperature difference basically. This is delta T, means the temperature difference. Now difference in what? This is an important formula. See. This is similar to that formula which you must have done in class 11. Linear expansion, superficial expansion, volumic expansion. Similar to that, this is variation of resistance with temperature. There also temperature varied length of any material. That's why you got LT is equal to L naught. Similar. Similar is it for the resistance. Now T is what? T is a certain reference temperature that is taken. So this is a certain temperature. Certain temperature means at a particular temperature you are calculating. So T naught is what? T naught is the room temperature. So surrounding or room temperature, this will be given you in the question. So T minus T naught is this. Similarly, resistance at this temperature T is the RT. This is resistance at temperature T. And R naught is the initial resistance. Initial resistance means what? Resistance at the room temperature. So this is the resistance at room temperature. Apart from this, you have one more thing, alpha. Alpha is mainly coefficient of your resistance, temperature coefficient of resistance. This is temperature coefficient of resistance. It depends on the material, nature of material. So different materials have different values of alpha. Alpha's value will be given in the question, or it can happen rest of the things are given and you need to calculate the temperature coefficient of resistance. It depends on material and its SI unit is Kelvin inverse in this. So this is the formula that you have to remember. R is equal to RT is equal to R naught 1 plus alpha T minus T naught. If the temperature difference is given to you, take it as delta T directly, multiply it with alpha. One more thing, with the help of alpha also you can decide the material, or if you have the material you can decide the nature of alpha. If it's a conductor, then the value of alpha is positive. If it's an alloy, again alloy, if it is alloy it will also be positive, but it's just that it will be very small. Small alpha means 0.0000 something value, means 10 to the power minus 31, or in this manner you can see for alloys. For semiconductors and insulators, it is negative. Semiconductors or insulators, this value alpha is negative. So if you know the material, you can easily figure out alpha if alpha is asked in your question. So you can see if it's a semiconductor, you have to add a negative sign, or if it's a negative sign given, then you can say it's a semiconductor, or the material could be insulator. Usually conductors are given. Usual alphas in your questions appear for positive only because they are for conductance. So do one thing, note down these points. This is just one liner formula, remember it. Let's do a question also on it. Formula based question also we'll try to do. But before that, note down the points. Is this clear? Variation of resistance, this part.
Yes, ma'am.
So note down all these portions, and if you have any doubts in between, ask me. So from here you have to write, no, conductors you have written. See, this question says what it says: an electric toaster uses nichrome wire for heating element. Means whenever this toaster, this is connected, this is at room temperature, the resistance is this. So you have the value of room temperature, you have the value of resistance at room temperature. When the toaster is connected to 230 volt supply, current settles to this much. So you have the current with you, you have the voltage with you. RT means the resistance at the different temperature. You can calculate it with the help of this. You have voltage, you have current, calculate that R. Then what is the temperature? So you have to find T. Alpha is not there. Take alpha is 1.7 into 10 to the power minus 4 per degree Celsius. So alpha is also in terms of degrees Celsius. No need to convert room temperature. Try to calculate T. See, it's a formula based question only. This question looks long because it's in a story form. Room temperature is given, resistance at room temperature is given. Temperature you have to find out. Resistance you can find out with this. Alpha is given, only T is the variable. So quickly all of you calculate and show me your answers. Fatima, you have submitted your assignment. I have received it. When did you get it? This assignment.
I asked for it just now, approximately 2 o'clock. I asked.
Okay. So, but you didn't get them from them. So you asked to them the resistivity
Yeah,
questions.
I asked.
Okay. Okay, I'll check it then. I have seen yours, all your assignment, previous assignment that we did. So I think from here, both the Fatimas have not submitted. Otherwise, others have submitted. Also, you had uploaded it on the portal, no? You had not sent it on the WhatsApp.
I think I sent it on WhatsApp also.
Okay, on the WhatsApp also. Okay.
I sent it on the portal and WhatsApp.
Okay. And Fatima Munir, why did you leave the class before doing the assignment and submission? Rest of the student also did it. Yes, Fatima.
Yes, ma'am.
Yes, you didn't do the assignment. You left the class. What happened? Was this a network issue or what?
Probably a network issue. But I joined class on the last class.
The last class when we were discussing assignment, when we were doing assignment, were you there? Because I didn't receive your assignment. Were you there? Or did you submit the assignment that we did in the class? I shared the screen and we did the assignment of drift velocity and Ohm's law. 3 questions were there. Yes, Fatima?
Yes, ma'am, I was there.
You,
But
so
I
you,
think I left in between because I got disconnected and then I joined back.
no, I'm asking, did you submit it? Because I haven't
did not.
received.
I didn't
Okay.
submit it.
Okay, all right. That's what I was just asking. Okay, Akifa. Yes, yes. Akifa has submitted her answer first and it's correct. What about others? You also please submit your answers. Atif, Fatima, Hamza, Hiba, Huzefa, Krishna, Kulsum. It's a formula based question only. Don't look at the length of the question. Good, Kulsum. Kulsum has also submitted. Her answer is also right. Okay, last 2 minutes. Hurry up. At least try to find out the resistance, other resistance using voltage and current and put it in the formula. See what's your value of temperature you're getting. Only T is variable here. It's a single equation with a single variable. All right, Hamza has also given his answer. So 3 students only, Akifa, Kulsum and Hamza. Okay, Atif. So there's a slight variation all the answers that you people are giving. Kulsum Akifa say 848, Hamza says 845, Atif says 847. So yes, the answer is around this only 844 to 847, but just check the exact value. I think it will be 847 only. Others also please confirm. What's the answer you're getting? Krishna, did you get any answer?
Ma'am, solving.
Solving, okay. See, in this question, it says what an electric toaster uses nichrome wire for heating element. When a negligibly small current passes through it, its resistance at room temperature. So resistance at room temperature means what? R naught. This what we took as the room temperature. This is 75.3 ohms, this much. T naught means the value of room temperature. This is given as 27 degree Celsius. Then the temperature, we don't know, we have to calculate, but RT is given. No, RT is not given. You can calculate RT with the help of V and I. So, yes, who is going to tell this? What's your resistance coming among these only? Hamza, you tell what's your resistance is coming. How did you do it? How did you calculate the resistance at room temperature, Hamza? Yes, Hamza? Okay, Kulsum. Yes, Kulsum?
R is equals to V by I 230 by 2.68.
Yes. It's V 230 divided by 2.68. Because this is V by I, R will be what? R will be V by I. So 230 by 2.68, this will be somewhat 85.8 ohms. That's why I was asking the people who have submitted their answers. Was it coming this much? Approximately, it would come around this much. 230 divided by 2.68. So you have RT with you. T is unknown. Alpha is also given. Alpha is given how much? 1.7 into 10 to the power minus 4. 1.7 into 10 to the power minus 4 per degree Celsius. So now what do you have? You just have the formula for it. RT is equal to what? R naught 1 plus alpha. Delta T means T minus T naught. So put everything in this formula. This is 85.8 is equal to 75.3. 1 plus 1.7 into 10 to the power minus 4 T minus 27. So once you solve this, you will get the answer approximately 847. Okay, noted down. Yes, class. Did that part? That question?
Yes, ma'am.
Now see the next topic that you have three major topics that are interconnected. One is your EMF, other one is your terminal potential difference, and one is your resistance. These are the topics that you have. So temperature dependence, that is the formula that is required. Now the first thing that comes here is the internal resistance of a cell. For understanding internal resistance of a cell, you have to understand the structure of a cell. How does a cell look like? So if you expand the structure of a cell, you will see that basically from inside, a cell consists of two electrodes, positive and negative, whatever you call anodes and cathodes are there. These are electrodes. And these electrodes are dipped where? These electrodes are actually dipped in electrolytic solution. So this I think you must have done in your electrochemistry, or you will do it in your electrochemistry. This is the electrolytic solution. So basically what happens, a cell comprises of these electrodes which are dipped into the electrolytic solution. Now these electrodes and the electrolytic solution, this offers resistance, which we call as the internal resistance. Why are we referring it to as internal resistance? The reason is that because you are having what? You are having the resistance which is offered by the cell and present within it. The resistance that is offered by the electrodes and the electrolytic solution, all this is present within the cell, no? So this resistance, this type of resistance, you call it as the internal resistance. So internal resistance, it's the resistance offered by the electrodes and the electrolytic solution. And many a times we draw it along with the battery. I'll show you how. First, understand the definition of internal resistance. So internal resistance, it's the resistance offered by the electrodes and the electrolytic solution. The electrolytic solution of the cell. Now, there are various factors on which this internal resistance depends on. It depends on the types of electrodes used. It depends on the kind of electrolytic solution you are using. It depends on the separation between the electrodes. So, on all these factors, this internal resistance depends. And these factors are given in your NCERT. So, it's better to know what are all these factors and on which factors or what factors can affect the internal resistance. Mainly these are the three factors. Try to find it on yourself also. Now, what I was telling you, how to represent it. See, in a cell, we draw it in this manner. This is a cell, and along with the cell, now we connect this resistor. This shows that this is the internal resistance of the cell. The cell will be having its own voltage. This will be having its own voltage. But we draw it in this manner. This shows this is a cell. This is mainly a cell. But in a circuit, we write it adjacent to the cell. And we call this as the internal resistance. This is the internal resistance. Many a times, and actually most of the times only, this is written and drawn along with the cell, adjacent to the cell that you have drawn. Or it can be in this manner, means connected towards the positive terminal. This will be the internal resistance. So internal resistance is what? Internal resistance is the resistance which is offered by the electrodes and electrolytic solution. See, resistance means just opposition, and resistance can be given by anything. For example, when electrons are moving in a wire, they can collide with the wall of the wire and stop the collision. So it means what? This is offering resistance. This is what the wall of the wire is offering resistance. So in a similar manner, you can have different substances which can offer different kinds of resistances. So all the resistors that are occurring within the cell itself, this is called as the internal resistance. Understand these three terms very clearly: internal resistance, terminal potential difference, and electromotive force. Electromotive force, let's see right now what is meant by electromotive force. You must have heard of the term EMF. If not, hear it today. EMF is basically the full form of EMF. This is electromotive force. But don't get confused with the name. It's a misnomer. Electromotive force is not a kind of force. It's not a force. Electromotive force, this is actually all the concepts and all the properties are similar to voltage. Don't ever confuse it with electromotive force. So it will be a force. It's not a force. You cannot apply all the properties of forces that you have studied. You have different kinds of forces. One force you have already studied, electrostatic force, in this class only, means in your 12th standard you already have it. Then you have gravitational forces. So those kind of forces have different properties. Electromotive force, this is not a type of force. It's just a name given by old people, and then we are using it because of the convention. We are just following it. So don't go by the name electromotive force. It's just the full form of it. It's actually the maximum potential difference that is offered in a cell whenever the circuit is open. Open circuit means off circuit. If I tell you there's a circuit, okay, let me tell you, there's a circuit drawn. The circuit is off, means we have opened the key. Key is not connected, means current won't be flowing, but potential difference will always be there. So that potential difference, all the properties and phenomena of EMF is similar to potential only. SI unit is also volt only. The way the SI unit of voltage is what? V, you write capital V, volt. Similarly, SI unit of EMF is also volt, because all the properties are similar to voltages. So EMF is what? It's the maximum potential difference that is across or applied across the circuit whenever it's an open circuit. I'll write down the definition first. It is the maximum potential difference across the terminals of a cell in an open circuit means what? Off circuit. The circuit is not working right now. In an open or off circuit. So how can you calculate? It's the potential difference across the cell. It means if I say this is a cell, so this longer line, no, this represents the positive terminal of the cell. So positive terminal means that this is always at higher voltage. And this shorter terminal of the cell, this shows that this is a negative terminal of the cell. So negative terminal, here the voltage will be low. So it will be having lower voltage. Now, how to calculate the EMF? EMF is what? It's the maximum potential difference. Difference means what? You have to take out the difference, that is, you have to subtract them. So EMF will be what? EMF will simply be VH minus VL in this manner. This is VH means voltage at higher one. This is voltage at lower one in this manner. Sometimes what can happen, lower voltage can be zero. Let's take the example. If I say this is 10 volts, this is 0 voltage. So EMF will be what? EMF will be 10 volt only. The reason is that there is no voltage offered by this one, the 0 one. So that's why when you take it as 10 minus 0, it will still come out to be 0. Or if you have any different value, if had it been 5 volt, then the EMF would have been 5 volt. So it's the potential difference that comes. Now, if this is the potential difference, then what is terminal potential difference? I told you, three terms are there which are very important: potential difference, terminal potential difference. What makes potential difference different from terminal potential difference? See, whatever you have studied about EMF, it's the same as that of terminal potential difference only. But what distinguishes both of them is that terminal potential difference is for a closed circuit, whereas your EMF was for an open circuit. Means terminal potential difference is the potential difference across the terminals of the cell in a closed circuit. Or you can directly say, this was what? See, EMF is what? EMF is across this cell. So cell will be having its internal resistance. What we have studied, the cell has its internal resistance. There's a resistance present in the cell because of the electrodes and electrolytes. So it means there will be an internal resistance. So you can say EMF is the potential difference across the internal resistor. Because basically here you have a resistor which you can draw also in this manner. If you have a resistor along with it, then the voltage of this resistor, that will be the EMF. But in case of terminal potential difference, terminal potential difference means potential difference across the external resistor. What is external resistor? First, let me write down the definition of terminal potential difference. So this is the potential difference across terminals of cell in not in an open circuit, in a closed circuit, in a closed circuit. This is in a closed circuit. So potential difference across terminals of a cell in a closed circuit. This is terminal potential difference. Or you can say this is the potential difference across the external resistors. Now, what is meant by an internal resistor? What is meant by an external resistor? If this is your circuit, let's say this is a resistor that has been connected. I think by now you must have had your practicals also, practical classes. So in your practicals of current electricity, you have a whole setup where you connect wires and rheostat and ammeters and voltmeters and everything. So I think by now some of you must have had your practicals classes. So there also you will see this. So a resistor is connected, a cell is there, and this is a closed key. So this resistor that is present, this is the external resistor which I'm referring to. This is the external resistor. And this is the internal resistor. And this is the cell with any other potential difference. Now, if I say the potential difference across this resistor, there must be potential or voltage across this resistor. If I say the voltage is 9 volt, let's take it for example, the voltage is 9 volts. And I say that voltage across this is, let's say, 2 volts. And across the cell, this cell, EMF of the cell is 10 volt. Now see, what is the difference between all three of them, whatever we have studied? Firstly, we had seen internal resistance. Internal resistance is the resistance of the cell within. EMF is what? EMF is the potential difference in an open circuit. This 9 volt that you are getting, this becomes your terminal potential difference. This is the terminal potential difference. This is the potential difference across the external resistor. These are what terms that you have studied till now. So few theory portion is also there before we move on to the numericals. First, note down till here. If you have any doubts, still ask me. Again, if you wish to clear anything, just ask me again. Then we'll do a small theory portion before moving on to the numericals, because you have to know a relation to connect all these three.
You can scroll up. Okay, so thank you.
So see, the way you have done that resistor, that circuit, similar you have the circuit. Now you have to identify the terms and few easy formulas. Now see how will you do it. This is an external resistor connected with the resistance capital R. This is the EMF of the cell. This is the internal resistor. So when the circuit is closed, current will definitely flow through it. Let's say current I is flowing through the circuit. So how will you calculate I? See, I, which is the current of the circuit, I is equal to what? Using Ohm's law. V by I is equal to V by R. Ohm's law is what? Ohm's law is V is equal to IR. So if we want to find out I will be equal to V divided by R. So yes, Kulsum, tell us what will I write instead of V from the circuit? Instead of V, what should I write? Yes, Kulsum, look at this circuit, which is representing your voltage.
R.
Resistor is same as voltage.
EMF.
EMF, capital E, exactly. This is your V. Atif, what will be the total resistance of the circuit? Atif? How many resistors are there? Fatima, what will be the total resistance?
Capital R plus small r.
Capital R plus small r. See, you have external resistor and you have the internal resistor only. This will be capital R plus small r. Now, in this circuit, you are able to see a single resistor, external resistor, capital R. What will happen if you have so many resistors connected? Then how will you get the answer? The simple answer is this: you will see combination of resistors. The way we have done combination of capacitors, even if there were 3 or 4 capacitors connected, we could get the C equivalent. Similarly, you'll get the R equivalent here. Even if there are so many resistors connected, ultimately you will get the 1 R equivalent. So if you have more than one resistor, put R equivalent here. In this manner you can get. So ultimately your formula will be what? E divided by capital R plus small r. Capital E is the EMF, capital R is the external resistance, and small r is the internal resistance. Now, if you have to calculate the potential difference across the external resistor, so potential difference is what? IR. So potential, let me write it. Potential difference across external resistor. Current is I, the resistance of the external resistor, it is capital R. If you have to calculate potential difference across internal resistor, so it will be current multiplied by the internal resistance, that is smaller. In this manner, you can calculate. Now, if you are asked to write down the terminal potential difference, so EMF is already given. You need not calculate EMF. EMF's different formula are involved when we will do magnetics. Because of motion of charges, you will get induced EMF and there. So you have EMF till AC, and you have also a chapter electromagnetic induction. So there we'll deal all with these things. Now, how to calculate terminal potential difference? This is basically the potential difference across the external resistor. So V will be what? V is equal to I capital R. Now I is what? I we have just calculated E divided by R plus small r multiplied by R. You can use this formula. Apart from this, terminal potential difference. This will be the potential difference, the EMF of the cell. This will be the EMF of the cell minus the potential difference across the internal resistor. Potential difference across internal resistance R. So EMF is what? V will be EMF is E minus potential difference across the internal resistance is what? See, we had calculated I small r. So this becomes your another formula. E minus I. E minus I smaller. So what all things you have? You have got the formula of current. Current is E divided by R plus R. You know the potential difference across both the resistors and the two formulas of terminal potential difference. You can use any formula. Both the formulas are correct. So note down these things. And one more thing. I'll give you a question, formula based question on this only. That we'll do. First note down from you. Fatma, first part is right, 2 amperes. Try for the second and third part as well. Others also. So Fatima has answered the first, second, third part. Oh, okay, good, Fatima. All are correct. Try for the fourth part. And Akifa has answered all the 4 parts correctly. Good, Akifa. Others also, Atif, Krishna, Hiba, Hamza, Kulsum, your answer. Huzaifa, you have not answered a single question today. Huzaifa, you also try this question. At least get the answer for the first part, current. Direct Formula 1. Last 2 minutes, then we'll discuss. Okay, good, Krishna. All the answers are correct. Yes, good, Fatima. So last part is also correct. Huzaifa, at least try for the first part. Huzaifa and Hiba, you both have not answered a single question. Good, Huzaifa. First part, you have answered it well. Atif, your answer is still missing. And Hiba also. Good, Hiba. Hiba has also answered. See, current, how will you calculate? Formula of current is voltage divided by resistance. Voltage is EMF of the cell, resistance is external resistor plus the internal resistor. Good, Hamza. First part is yours is also correct. So, Hiba, tell which EMF did you take? What is the value of E that you took? Hiba? Yes, Hiba? 22. You took it as 20. And Hamza, what's capital R that you took? Hamza, what is the value of capital R that I should write? It's 10. Good. It's 10. And the internal resistor, this is 1. So this is 22 divided by 11. This gives 2 ampere. So first part, almost everyone has submitted. Is Atif not there in the class? Atif? All right, now the second part. Okay, Fatima. Fatima, you explain us the second part. How did you solve it? Fatima.
Teacher, external resistance formula is I into capital R. So I is 2 ampere. So 2 into capital R is 10 ohm. So 2 into 10, 20 volt.
Exactly in this manner. Potential difference across external resistor. Potential difference across the external resistor. This is the current multiplied by the external resistance. So current is what? Current is 2 amperes, resistance is 10 amperes. This becomes 20 amperes. In this manner, you had to calculate. Kulsum, did you try all the parts?
Yes, ma'am. Did you not get any of my answers? Only
No,
the
Kulsum.
fourth one I haven't done. I've submitted the first three.
Akifa, Fatima, Akifa, Krishna, Huzaifa, Hiba, Hamza. No, Kulsum. Did you submit it to me or to the host or?
I have submitted it to you, ma'am.
Okay, okay. So, okay. Doesn't matter. It's okay. If you have tried, then that's good. So, Kulsum, you only explain us. How will you do the third part?
I into smaller.
I into small r. Good. So, potential difference across the internal resistor. Potential difference across internal resistor. This will be I multiplied by small r. So I is 2 amperes, small r is 1 ampere. So this becomes what? Again, we get 2, not 2 amperes, 2 volt. Here also it will be volt.
Teacher, in the second one, yeah, okay. Nothing.
Voltage. No? Then you have to find out the terminal potential difference. See, in the fourth part, terminal potential difference, you can do it in two ways. We have seen two formulas. One is what? E divided by R plus R multiplied by R. So E is 22, capital R is 10, small r is 1, multiplied by capital R. Capital R is 10. So this is 2 multiplied by 10, which gives you 20 volt. Or we have one more formula of it. V is equal to E minus IR. EMF is what? 22. Current is 2 volt. Small r is 1. So this is 22 minus 2, that is 20 volt. Both the formulas will lead you to the same answer. All right, so those who haven't noted all the parts, just note it down. Done? Written?
Yes, ma'am. Ma'am, could you explain the difference between EMF and potential difference?
See, EMF and potential difference. Just a second. See, the very first difference that comes between EMF and terminal potential difference is the kinds of circuit. So I hope you know the difference between an open circuit and a closed circuit.
Yes, ma'am.
All right. See, in an open circuit, whatever is the potential difference, maximum potential difference between the two electrodes of the cell when no current is drawn from the cell. When no current is drawn means when it's an open circuit. Whereas terminal potential difference is what? It's the potential between any 2 points in a closed circuit, any 2 points. But this is what? This is the potential difference across the terminals of the cell. You always see EMF written over here. And potential difference, this can be taken between any 2 points in the wire. Also, this EMF, this is independent of resistance. This EMF, this doesn't depend on the internal resistance or the external resistance. EMF, whereas in case of terminal potential difference, it depends on the resistance, because we can take any 2 points and whatever resistance will come in between, that will affect your potential difference. Apart from this, you have to remember that EMF is only used for the source, means source of the cell, as in when I'm talking about the cell, only for the source. If this is the source that is generating, then I'll be using the term EMF. I won't write the voltage. Whereas in the circuit, if I talk about difference over here, this can be the terminal potential difference. Terminal word we use when we refer to a closed circuit. Closed circuit means when the current is drawn from the circuit. And always remember that this EMF, this is always greater than the potential difference between any 2 points in a circuit. Potential difference, that this terminal potential difference which we have studied, this is greater than this EMF when the cell is being charged, which we'll see in the next class, charging and discharging. That makes it the major difference. So EMF is the maximum potential difference, all the maximum value that can occur in a circuit. If I take any 2 points, or if I take, let's say I've taken A point and I have B point, whatever is the potential difference between these 2 points, that will be the potential difference, because VA will have a potential, VB will have a potential. But whatever is the potential of this source, means of the whole circuit through which it is generating, then you call it is as the EMF. So the term EMF is used for the source of electric current. EMF is basically the cause of it. Potential difference is the effect of it. Because of the cause generated, this EMF has been generated. That's why we are getting these potential differences. Is this clear?
Yes, ma'am. Thank you.
Now, let us just discuss the previous assignments that you all submitted. Akifa is there, no? In this class. So Akifa also did all the questions. Okay. So yes, Akifa's assignment 43. Good. Akifa is correct. So let's discuss it from here only. Or okay, let's discuss it student by student. Hanifa is the Fatima didn't submit, no? Krishna did it? Krishna did it. Okay. So okay, Krishna, you have also done all the questions.
Yes, ma'am.
The answer of third one, this is 43.34. It's 48 coulomb B part. So, oh. 6 to 10 to the power minus 6. This is integration. See, whenever you are given charge, for example, charge is given to you with some variable 3t square plus 2t somewhere, then you have to calculate the current, then you differentiate it dq by dt in this manner. But if you are given current, for example, in this question, the way in this question it is given 4 plus 2t. So now you have to find out what? You have to find out the charge. So if I is equal to dq by dt, charge will be what? Charge will be I multiplied by dt. So here you have to integrate it from T1 to T2. This is the formula that you have to keep in mind, and then you will get the answer. Fatima Mahir, Hamza did it. Okay, Hamza's is also correct. Good, good, Hamza. All the questions he has done it. 2t cubed by 3t. 3t square by 2 plus 1. Okay, t 5 minus 3. Okay, okay. Hamza. See, Hamza, whenever in your subjective papers, no, you do these calculations. Show your calculations till the end step, the way you have got this answer. So when you had put the values of the upper limit and lower limit, show till that step. Otherwise, rest of it was correct. Atif. Atif is there. I is equal to Q. Okay. 43.34T8. See, in this manner, Hamza, I was referring to this. In this manner, you have to show. If you are integrating it, then this step has to be there. For example, you left it, this step was missing. Sometimes what happens, you can lose your marks. So till your last step, you have to show your calculations. This is incorrect, Atif. From low potential to high potential is not correct. From high potential to low potential. High potential to low potential. Heba did it? No, Heba didn't do. Heba, you have not submitted the previous assignment. Kulsum. Yes, Kulsum is there.
Ma'am, in the third question, it's 2 by 3, ma'am. I accidentally cut and wrote 4.
2 by 3, this
Yes.
portion, no? So 4 you have written?
Yes, I accidentally wrote 4. I was confused. It's 2 by 3.
Okay. The final answer is also right. 25. The interval was 2 to 6 seconds. This, yes, 2 to 6 seconds. This is 40. This is 2 by 2 t square. No, this is correct, and high potential to low. And Josefa also gave the assignment? Yes, Josefa also. Number of electrons. Third question, Josefa. Now is the third question clear? Let me discuss the third question. Rest of them are given. See, whenever you give the answer, 48 coulombs, don't miss the SI units. The way you have written ampere, electrons in this manner. See, someone who did it. Atif did it. Yes, Atif did it. Third question. See, Josefa, current is given to you. Time interval is given to you. 3 to 5 seconds. Again, you have to find out the charge from here. So charge will be what? Integral of 2t square minus 3t square means whatever is the current given to you. You have to integrate it. And then at the last step, when you'll put in the limits, 2t cubed by 3 minus 3t square by 2 plus t, when you'll put in the limits, see, 2 by 3 will be here. T cube, you have 5 cube minus 3 cube. Then minus 3 by 2, then t square. T square, you have 5 square minus 3 square plus t, that is 5 minus 3. Then you solve it and you get the answer as 43.34 coulomb. Josefa, is this clear?